Hello everyone, and welcome to the MathDBase.com Anicasts series. I'm your host, John Kisiedu. In this installment in the Calculus series, I'm going to discuss tangent line approximations, a method of approximating values of a function with values on a nearby tangent line. If f is a differentiable function, that is smooth and continuous, the slope of the secant line through the points x1, f of x1, and x2, f of x2 approaches the slope of the tangent line to f at x1 as x2 approaches x1. So if x2 is close to x1, the distance between f of x1 and f of x2 will be almost equal to the distance between x1 and x2 times the value of the derivative at x1. The value of the function at x2 can be approximated by adding the small increment obtained from the distance between x1 and x2 times the value of the derivative at x1 to the value of the function at x1. The closer x2 is to x1, the smaller the increment will be. This is the point-slope equation of the tangent line to f at x1, and using this formula, we're taking the y-coordinate of a second point on the tangent line at x2 as the approximate value of the function at x2. The error in using a tangent line approximation is calculated by finding the difference between the actual value at that second point and the approximated value there. How accurate a tangent line approximation will be depends on three factors. 1. The nature of the curve. Some curves grow very quickly, such as a polynomial like x to the fourth. Exponential curves, such as 10 to the x, grow even more quickly, so a small change in x can bring about a large change in y value. On the other hand, log to the base 10 of x is a very slow-growing curve, in that y values don't increase much even for relatively large increases in x value. Of course, if the function is a line such as 5x, a tangent line will coincide with the line at every point, so the approximation will be exact. 2. The part of the curve on which the approximation is being made. Even fast-growing curves can have sections that are relatively slow-growing, such as the part of y equals 10 to the x for which x is negative. 10 to the x gets asymptotically close to the x-axis as x approaches negative infinity. As x moves closer to 0, but is still negative, the rate of growth increases, but is still very slow compared to the part of the curve for x greater than 0. Similarly, log to the base 10 of x is a very slow-growing curve, but as x gets close to 0, the curve approaches the y-axis asymptotically at an increasingly fast rate. Given x to the fourth for x less than -1 and x greater than 1, the curve falls or rises very quickly, but between -1 and 1, the curve is very flat and falls or rises very little. 3. The size of the interval. Even for a fast-growing curve such as y equals 10 to the x, if the change in x is small enough, even on a fast-growing part of the curve, a tangent line can be a good approximation to the curve. The actual value of 10 to the x at x equals 4.95 with an interval of 0.05 from x equals 5 is 89,125.0938 to 4 decimal places. The approximate value is 88,487.0745 to 4 places, for an error of 638.0193. Given the values of the function near x equals 5, an error of that size is quite small.